Hello, my name is Shelton. I am a rising senior at Wake Forest University, majoring in computer science and mathematics. In this summer, it is my honor to work as a summer scholar in the Carnegie Mellon University Robotic Institute with Renos, Joseph, Simon, Dana, and Dr. Sikra. My summer project is about addressing high-level concept limitation in concept bottleneck models with residuals and vector disentanglement. What is a concept bottleneck model? Compared to a traditional image classification models, the concept bottleneck model improved the interpretability of deep neural networks actually by predicting a set of high-level concepts in the intermediate layer that are understandable by a human and output those concepts to a model and perform the classification. So recent studies show that reducing the number of concepts actually causes the model to perform poorly, but actually in our study, it is not. In practice, insufficient concepts are available to represent the entire feature space of the dataset, leading the model to learn the representative representation from the dataset and causes potentially poor performance. And also, high number of concepts induces additional noises to compromise the interpretability of the model as well. Our study showed that the model can effectively utilize a smaller important concept set to perform the task without sacrificing the performance. With a smaller subset of concepts that degrades the performance, using a residual layer and vector disentanglement methods improves the models to the performance of the full concept size. Our works involve three methods to improve the interpretability of neural networks. The first method is to calculate the feature importance. The most well-known method is the sentencing map, but it only calculates the local feature importance, which is not always reliable. So we decided to calculate the global feature importance in our study, for example, test time activation vector, but it requires additional supervised classifiers to prepare for the concepts. So we decided to use the integrated gradient. And also recent studies about concept bottleneck models try to improve the limitation based on the original proposed study of concept bottleneck models. The postdoc concept bottleneck models actually addresses the lack of highly densely annotated data sets. And the concept bottleneck model with the unsupervised concept actually addresses the problem of lack of sufficient concept size. And there is a study that addresses the leakage problem in concept bottleneck model that to improve the interpretability, interviability. So another method that we are using is the latent-based disentanglement methods. The recent study only focused on maximizing the mutual information between the inputs and target prediction, which is not always the case in the classification task because the inputs might be just not useful for the target prediction. So here in our study, we propose a mutual information estimator to minimize the mutual information between the residual and the concepts to make the information more reliable for the task prediction. So here is the proposed architecture. We fine-tune an inception V7 model to learn the embeddings from the datasets. And we have two multi-layer perceptrons to map the embeddings to a subset of concepts selected by calculation of feature importance by integrated gradient and output in another multi-layer perceptron to output the residual, which is basically unsupervised concepts. We then concatenate the concept and residual to a logistic regression to predict the bird species. Meanwhile, to avoid overlapping information between the concept and residual, we additionally train a mutual information estimators that outputs first the learning loss of the estimator itself to optimize the parameters in the estimators and the estimated mutual information to minimize the mutual information between the subset of concepts and residual. During the back propagation, the multi-layer perceptron of concepts is only optimized by the concept loss. The multi-layer perceptron and the inception V7 model is optimized by the estimated mutual information and the task loss. So what is the integrated gradient for feature attribution? The integrated gradient of a specific input feature is calculated by integrating the gradient of the model's output FC with respect to the input CI, which is which is a specific concept feature over a straight interpolation path from a baseline C prime, which is just 0 to the feature C. And this is the feature importance that we calculated. So we incorporate the mutual information estimator based on the contrastive learning to our model architecture. And actually, the mutual information estimator predicts the conditional distribution of the residual given the concept. So therefore, we can know how can we learn about the residual from the concept to estimate the mutual information between them. And 254 neural networks are used to predict the mean and log variance of the distribution. The negative log likelihood for the distribution is computed to optimize the estimator. Meanwhile, the estimated mutual information is computed through the contrastive learning to decorrelate the concept and residual layer. So the first result is that from figure A, we could see that with a decent subset of important concepts, the model's performance is not affected. We can tell from like the concept size around like 40, the performance is actually very good compared to the performance of the model with the full concept size. The second finding is that with a smaller subset of important concepts and residual, the model performs on par with the model with full concept size, and the residual layer is more effective with less concept sizes. And we could see from the first figure that with a low concept size, actually there's a sufficient decrease in performance of the model. So here we introduce residual layer to compensate for additional information in the data set that is not encoded by the concept layer. So here we could see that with the residual size of 0, the performance is really bad. But with the introduction of residual, the performance starts improving and starts actually converges around a residual size of 4. But actually, they are still decreasing in terms of the task error rate. So like more specifically for the concept size of 20 and residual of 8, it actually is pretty, like the value is pretty similar to the baseline of the full concept size. So here we actually showed that with a small subset of concepts and the help of residual, the model actually performs on par with the model with full concept size. And also the last result is about the mutual information estimators. Because we add the residual layer to encode additional information from the concept layer. So we don't want there's overlapping information between those two layers. So we incorporate a mutual information estimator to decorrelate the concepts, and potentially we want to improve the model performance with large residual size. So this table shows the percentage of improvement of the model after the incorporation of mutual information estimator. And we could see that with a higher number of residual, actually there's a greater percentage of improvement after the incorporation of mutual information estimator. So we conclude that the mutual information estimator to decorrelate the concepts and residuals improves the model performance with large residual size. At last, I want to thank Rachel and Dr. Dolan for the support of the entire REASE program and make everything possible. And also, I would like to express my appreciation to my mentor, Renos, for the entire support and instruction during the program, and Dr. Sikra for the idea and instruction, and all other lab members and REASE faculties and sponsors for helping me. Thank you.